I'm Till. I'm working at Data Artisans as a software engineer, and I'm also a Flink committer. And today I want to tell you a little bit about dynamic scaling and how Flink can handle changing workloads. So let's get started. So first, let's take a look at the usual Flink job, which does real-time data analytics. So processing real-time data, everyone who has done that knows that the input rate of your data is not necessarily constant. So it usually depends on time, because your customers are not equally distributed over all time zones or on some external events. So when writing these kind of real-time analytics jobs, you have to take that into consideration, especially if you've committed to some SLAs. So for example, if you've promised your business analysts that you will update their dashboards with the latest business intelligence within the given time interval after the data has arrived, you should better make sure that the processing time is not so affected by the incoming data rate. Or another example is if you want to do like online recommendations for customers who are visiting your online shop, for example, you're interested in doing these recommendations while they are still on your site shopping, not after they have finished their shopping tour, because then the recommendation is not so useful anymore. So as someone running these kinds of jobs, one has to think about how many resources one dedicates to the execution. So they're usually, because Flink used to offer you only the possibility to start the job with a fixed set of resources, you have to find a trade-off, or used to find a trade-off between over-provisioning not too much, because that would be a waste of resources and waste of money, but also not to set the resource limit too tight, because then it will often happen that you violate your SLAs and make your customers unhappy. So with the old Flink, as I said, you had to select the degree of parallelism when you started the job. And once the job was started, it was not possible to rescale it while keeping the state of the job. So having this kind of fixed number of slots or CPUs on which you run your job, this will always mean that there are times when you're over and under provisioning with respect to the current workload. So what you actually want to have is a system which adapts dynamically the resource consumptions to the actual workload. Because if that's the case, first of all, you don't have to worry about with how many resources you start your job, because it will adapt to it. And this will allow you to hopefully always meet your SLAs and saves you a lot of money, because you don't have CPUs idling around. And that's exactly what I want to talk, or what I want to show you in this talk. I want to show you how what the problems are when trying to rescale Flink jobs, how we solved the problems. Then I want to show you what the current state is by giving you showing you a short demo. I hope everything goes well with that. And last but not least, I will tell you a little bit about what the next steps, development steps, are going to be with respect to dynamic scaling. So let's talk about dynamic scaling. The really simple and basic underlying idea is that if things take too long, you allocate more resources, spread the workload across these new machines, and make your job finish faster. Of course, this has the assumption that your job is parallelizable, or the thing you want to achieve, want to compute, basically. For the rest of the talk, I want to assume that, because if your job is sequential by nature, then dynamic scaling won't help you to deal with excessive execution times. So in the context of Flink, where you have topology of operators which are executed in parallel by instantiating tasks which are distributed on the set of available machines. Scaling up and down means to instantiate new subtasks or kill subtasks. So if we have like this simple stateless job where we have a source, a mapper, and a sink, and when we see that, for example, the mapper is constantly busy and can't keep up with the workload, scaling up would mean that we instantiate a new mapper subtask, tell the source about its existence, so that the sources can now distribute the workload across all 3 mappers instead of 2. And the same basically applies to scaling down. So when we see that the mappers are actually idling, then killing one could help to keep the remaining mapper, which is now responsible for the whole workload, busy again. So that is quite, I mean, the scaling these stateless jobs is quite simple. However, usually all the interesting jobs you might be interested in executing are stateful. At the very least, if you want to assure fault tolerance, for example, there you have to store, for example, the sources where you are currently in your Kafka topic or the position in the file, so that in the case of a recovery, you can continue from that point. So that's why we actually have to think about scaling stateful jobs. So when scaling stateful jobs, there's the question, how do we initialize the state for the newly created mapper? What should it be? I mean, it's conceivable to instantiate it with a default value, or to derive the state for the new mapper from the existing state. Depending on the use case you have, either of these possibilities might be correct. So for example, if you have 2 counters which count, and you want to instantiate a new counter, you could initialize the count value, which is the state, to 0, or you could subtract, for example, some values from the existing state and add it to, or and start the new mapper with a subtracted value, for example. So that's actually the question we have to answer before we are able to scale jobs. But before we look into how we do that, I just want to quickly talk about the different notions of state in Flink. Because when we talk about state, we actually distinguish between 2 types of states in Flink. On the one hand, we have the keyed state, which is basically a state value which is associated to a key value, which is extracted from a stream record by a key selector function, which is usually specified, or which is specified in a Flink topology by the key by operator. So whenever you have a key by operation in your Flink job, which is followed by an operator which does some state processing, stores some user-defined state, or does, for example, windowing, this state is stored as keyed state, because the generated state is associated to the key, which is derived from the incoming stream record. That's the one type of state we have. On the other hand, we have the non-keyed state. The non-keyed state is basically bound to the subtask of the operator. So we only know, like if you have a Kafka source, for example, it stores the offsets as non-keyed state, and the system just knows that there's some state which belongs to the Kafka source with index x, for example. And these 2 types of state, we have to be able to repartition in order to be able to dynamically scale our jobs. So how do we do that? Well, let's first take a look at the keyed state. The repartitioning of keyed state is similar to consistent hashing, or the basic idea, because what we do is we have the key space, and we split the key space up into several groups. such that every element maps exactly to one key group. And now when we execute a program with keyed state, we assign each subtask a range of key groups for which it is responsible. And all elements with a key falling into one of the key groups of this subtask are going to be routed to this subtask, which processes the element. And by doing that, rescaling actually simply means changing the assignment of key groups or the mapping in the system. So if you take a look at this example here, we have like again a simple source function and two mappers, and we've separated the key space into 4 groups. And now we assign the first and the second key group to the first mapper, and the third and the fourth key group to the second mapper, which is responsible for these key groups. When we now want to scale up, add a new mapper, for example, we can simply take, like here in this case, we took the second key group, the orange one, and assign it to the new subtask, which we've instantiated. And now this subtask is responsible for all keys which fall into the second key group. Of course, what you see now, or what you also see at this example, is that the maximum degree of parallelism of an operator is limited by the number of key groups. Because here in this example, we could scale up another time to a DOP of 4. But then it would mean that every operator has only one key group assigned. So when we now try to scale up to 5, for example, there's no key group to assign to the new subtask, and thus it won't process any elements. That's why you have to specify at the startup of your job with how many key groups you want to execute the job, which will set the maximum degree of parallelism to which you can scale up. But usually the value is you set it high enough to have some room for scaling. Okay, that is the general idea of repartitioning keyed state. For the non-keyed state, there are actually different approaches possible. The one approach is to let the user actually define the splitting and merging behavior of non-keyed state, because he's aware of the state which is stored in the operator and possibly knows how to split it. So by providing a split and a merge function, it would be possible to split the state up or merge it. However, even though that's the most general approach, it's also error prone, because the user has to define this function, and that's where things can go wrong. And the system has to execute additional code to do this rescaling operation. So the approach we've chosen for Flink in the initial implementation of dynamic scaling is that we break the non-keyed state up into smaller units, which are visible to the system, so that it can repartition the non-keyed state with respect to the units. Of course, the requirement is that the non-keyed state contains multiple entries, like which you can split up. For example, a counter value would not be possible, but as we will see later, the Kafka source state, where we store partition offsets, is easy to split up. And once we have these smaller units, the system can take care of the rescaling without having to know what the state actually contains. So what's then happening behind the scenes when you rescale your job is that handles to these state units, non-keyed state units, are collected at the job manager. And upon rescaling, there are different repartitioning schemes possible to do. Either you split the set of state units up into as many groups as you have operators or subtasks for an operator, or you could also think about like just collecting all of them and broadcasting the union non-keyed state to all new instances, so that the instances themselves can pick what they need from the state. This is both conceivable, but we've implemented in the first version the repartition and send scheme. So to make it a little bit more concrete, let's take a look at the Kafka source. So the Kafka source has its task is to read data from a Kafka topic, which means that every subtask of a Kafka source operator is responsible for a set of partitions which it reads and forwards the read data to the downstream operators. So on the left side, we see how it was implemented in the past. There we basically, every Kafka source stored the offsets for all partitions in just one blob, which it persisted when the checkpoint was taken via the state backends. But the system was not aware of the fact that there are actually multiple partitions stored in one blob, but it just knew that this blob belonged to the specific subtask. What we changed now is that we store now each partition offset with a partition ID in an individual unit, so that the system can assign the partitions to other subtasks as well. And that way, we are actually able to scale non-keyed state. Sorry. So since that was a bit theoretic, let's take a look at a concrete demo. What I want to show you is that we can actually rescale this kind of job. What the job does is the following. It reads integers from a Kafka topic, keys by the integer value, and counts how often we've seen each integer value. And this result is then written to another Kafka topic. So what we're actually calculating here is some kind of running aggregate of integer values. So quite simple. But here in with this simple topology, we already have, like, for the Kafka sources, we use non-keyed state, and for the counters, because they are the following operator after a key by operation, we actually use keyed state. So we have to be able to, in order to scale this job, we have to be able to scale keyed and non-keyed state. First, I want to start this job with a parallelism of 1, so that it can't keep up with another Flink job which produces into the Kafka topic. So that I hope that we see that the lag of this Kafka sources is constantly increasing because the job can't keep up with the producing rate. Then I want to show that we can take a save point and rescale and scale it up, so that the Kafka lag is no longer increasing and maybe eventually will decrease when the job catches up with the producer. So let's see. Well, this is working. I have to change. Where is my mouse? Wait. We'll start the mirroring so that I see what you see. All right. So at first, I will start a Flink cluster. Okay, now we have a Flink cluster. Let's take a look. Here it is, where we have one task manager with 5 slots. I will first use 2 of these slots to start the producing job, which will constantly produce or emit random integers to the Kafka topic. And in the other 3 slots which are left, I will first start the job with the DOP of the consuming job with the DOP of 1, and then increase or scale it up. Okay, let's see. So first I have to start the producing job with a parallelism of 2. So I hope you can read it. It's Flink 1 minus P2. Then I specify the class I want to start, which is the called producer. Now I have to find the jar, which is here. Wait, this one, and start the job, which is hopefully, yes, it's running. We can also convince ourselves that there's something happening in the web interface. Here we see only 3 slots left, and there's one job running, which is the producer here. All right. Now I will start the consumer. As I've said, with the first with the DOP of 1. Which is the default class in this jar, so I don't have to specify the class name, which is running now. All right, so let's take a look at this job. Now we have 2 jobs running, 2 slots still available for our dynamic scaling, and we can take a look at the job, and we see that is doing something here. It is read some data and sent some records. I've artificially slowed it down a little bit, but this applies to the producer as well as to the consumer. So yeah. Okay. Now what I've started the cluster with is with the I've configured the graphite metric system so that the Flink logs the metrics to graphite, and I now use Grafana to show you the consumer lag of the Kafka sources. So let's see. I've already prepared something. So I have to specify that we want to a metric, the Kafka lag, which is on our task managers. Then I select the Kafka consumer job and take a look at the sources. And the sources should expose the lag, the record lag. Wait, let's see. Records lag max, exactly. And I want to take the maximum because later I will start the job with a higher DOP, and then we have several of these things. And we see, I hope you see it, that the Kafka lag is constantly increasing because we are basically consuming at half the rate at what we are producing. We can take a look at the comparison of these of the producing rate and the consuming rate as well. You just have to add some more queries. So we select from the task manager. From this time from the producer, the sync exposes the Kafka producer, which is here, and there we select the records send rate metric, which is basically just forwarded from the from Kafka metric, and we want to sum it up. Sum series. Okay, that is basically the rate at which we are producing, which is 20. Now I will add also the consuming rate, which is this time we select the consumer job, select the source, again the Kafka consumer, and select the records consumed rate and sum it up again. All right, so let's take a look at, well, that's the Kafka lag, and that is the consumer producer weight. The green one is the producer, and the yellow one is the consumer weight, where we see that is somewhere alternating around 10 events per second. That's because I've slowed it down. Okay, so like an increasing lag would be an indicator for under provisioning of your job. So we should try to scale it up. Let's do that. Okay, for that, we first have to look the job up. So to find out the job ID, and that you can do by running Flink list, which gives you here the job ID of the consumer task. For that, we first take a save point because we want to resume with the changed DOP later on. Simply Flink save point with the job ID. The bottom of that is now we have taken a save point with this path, and now we can cancel our job to restart it with a changed DOP. Okay, now, oh no, wait, that was wrong because I've provided not the job ID but the path to the save point to cancel the job. All right, to verify that, we see here that something has thrown a cancel exception. All right, now let's start the job with a different DOP. It's again the same command, but this time we want to start it with a parallelism of 3, and we provide the path to the save point, which is that one. And now, hopefully, the system starts with a DOP of 3. Let's see. All right. Looks quite promising. There we have some things. 103, 203, 303. Let's take a look at the web interface. First here. We go one back. So again, now we have 0 slots left, 2 jobs running, and the consumer. Let's take a look at the sources. Now we have 3 sources. Everyone reads some data, which, yeah. So we have now 3 Kafka sources waiting for Kafka. So now what should happen in Grafana, we should see that the lag is actually not increasing or in fact decreasing. So we should give it some time and then it should decrease. At least it's not increasing anymore. Let's see until the when the Kafka metric system realizes that, oh yes, that we are consuming faster than we are producing. That looks good. I guess these like stair artifacts are because of the update rate of the how often the lag is computed, basically. You can also take a look at the consuming rate. Here, it also takes some time until Kafka realizes, or the Kafka metric is updated. That was also in my dry runs before. I can promise you that at some point of time it will switch to 30. Just have to give it enough time. But we see that the lag is decreasing, and we've also seen that the job is now running with a DOP of 3. So that's actually what we wanted to do. And maybe I can let it run, continue with my presentation, and at the end we can take a look whether the rate is actually went up to 30. Or maybe I did something wrong with the sum operation. Let me just check. Oh, it looks actually okay. It should be updated soon. Okay. Yes, so, oh yeah, now it's increasing, you see, up to 20 and now up to 30. So, as I've promised. All right, let's switch back to the presentation. Here we go. All right. So what you've seen is that you can manually scale Flink jobs now. So the process is you usually take a save point to be able to resume from this point of time. You stop the job and then restart the job with an adjusted parallelism and this save point to scale it up or down. This works, and one can write a script which automatically performs that, but it's not complete yet. So when you perform the save point and actually cancel the job, there's a gap in between. It's not an atomic operation, so things can happen in between. Like, for example, side effects, writing data to an external systems, which you don't want to happen. So what we want to add next is a stop signal, which stops the job and takes a save point with the last data it has seen. That way, it allows you to shut down Flink jobs in a clean manner. Then next, we've seen that we had to stop a job, which is in some cases not tolerable. And in order to keep the downtime low, we want to add that we can scale individual operators on the fly while the job is kept running. And last but not least, you've seen that I started the Flink cluster with some additional slots which weren't used in the very beginning. So at the moment, in order to scale up, you have to do that. You have to start the job with enough spare slots. Otherwise, there won't be enough slots left to scale up. But currently we're working on adding dynamic container allocation and deallocation with the Flip 6 improvement, which will basically refactor the process and deploy model of Flink a little bit, so that one can allocate these new containers from a cluster manager like Yarn or Mesos. If you want to learn more about that, I can recommend you to go to Running Flink Everywhere, to this talk, which is given by Stefan Even at 4:45 at the Kesselhaus. And last but not least, I think that auto-scaling policies to automate the scaling process would also be quite nice, so that you are able to define some metrics and thresholds for these metrics when the system should scale up, like, for example, latency, throughput, CPU utilization, or any other metric you can think of. This is actually not too far-fetched, because there are already systems out there which offer the functionality for that, like Kubernetes, EC2 or Mesos allow to automatically scale services, and maybe it's just to plug Flink in there. We have to see. So this brings me to the end of my talk. So what you've seen today is you've seen the challenges of scaling Flink jobs, which is mainly handling and scaling keyed and non-keyed state. You've seen that we use a key group approach for keyed state, and for the non-keyed state that we try to split the state up into smaller units. Then you've seen that it's actually working. It is, however, not yet merged into the master. It's you can find the code in the under this branch there. But I can promise you that these features, what I've shown you today, will be part of the 1.2 release. So actually, I assume that this will be merged in 1 or 2 weeks. And future versions of Flink might support scaling on the fly of individual operators with automatic policies. That's, I guess, a feature which is quite nice to have. And with that, I'd like to finish my presentation. Thank you very much for your attention. And if you have questions, then feel free to ask them now.
Hello. I wonder how do you handle if to combine the two stuff or the talk before and now. So if you experience a failure in your topology and you have to recover from a state in which you need to scale up with respect when you failed. to keep up with the replay of, for example, in this case, you have Kafka. Then when you reconnect, it starts pushing the tuples you lost. So if you stay down for a lot of time, you need to scale up to manage the load.
Yeah, to catch up with the produced data.
Okay.
How we manage that at the moment, we don't do it automatically at the moment, because as I've said, the scaling happens manually. So you at the moment would have to have like a script in place which does it probably. But in the future, with when these kind of auto-scaling policies are in place, you could also think of using like the Kafka lag as a metric for scaling, and then in case of failure, the system would just apply the usual recovery logic, and then at some point of time it will notice that wait, I'm actually too much behind the current head of the Kafka topic, so I have to scale up by having these auto-scaling policies. That's basically it. So it's just two functionalities there. Like the recovery is just as you know it from Flink, and then just having the scaling policies which trigger the scale up thing. Yeah.
Thanks for the talk. I wanted to ask that when you were talking about the keyed groups, when you're doing by keyed states, if we have like more partitions available, more parallelism available, would it automatically divide the key? Like if in a one keyed group I have two keys, would it automatically divide the keyed group into two separate, like one keyed group having one key and the other, and if I have more partitions available for?
No. At the moment, there's no way to change the number of key groups once you've started the job. What you basically do when you write a job, you set a parameter value which is called max parallelism, or what we call max parallelism, which defines the number of key groups, and that is static, so that won't change, but it could be the case indeed that once you start writing a job, you think that wait, it will never be exceed like the parallelism of 10, for example. So I set the number of key groups to 10, and later you realize, wait, now actually I need like 20 subtask instances to cope with the workload. We will probably add some tools to take a save point and split the save point data up into more key groups, so to make it portable, that you can also later on adjust the max parallelism. But at the moment, it's in the current version you have to define it first. Per default, it's 128. And this doesn't change.
Thanks.
Yeah.
How does the trade-off look like with this max parallelism parameter? So can that just set it to 1 million, or that slow down much or what?
I guess that depends a bit on your job specifics, how many keys you have, how large your state is. The overhead of managing these key groups is, there is some, but it's kept at a minimum as far as we could. What we haven't done yet is running benchmarks between the old version where we didn't have introduced the key groups and where we've introduced the key groups. But I think that the overhead is negligible with respect to the usual I/O waiting time you have in your job. So that should actually not be shouldn't impact the user too much.
What about snapshots?
No, we don't. We actually, what we do is we snapshot the state of each subtask into one file. And when we scale up, for example, then we basically store for every entry in this file an offset, then assign different offset ranges to operators, which in some cases share then the same file, or read from the same file, basically, which of course has to be stored in a network accessible storage, like HFS or so. Yeah.
Just one more question about the last feature that you mentioned, automating rescaling policies, which I guess when you talk about scaling is one of the most interesting features that people who work in operations are looking at, because fiddling manually with the parallelism and so forth is a big pain. So is there any ETA on this feature, or is it something that you're working on, or is it just something that's on a wish list and will come in some distant future? Thank you.
Well, I mean, I can only talk for myself, right? Not for the project or for the community. I mean, the community decides what the priorities are. I also think it's a really nice feature and important to make dynamic scaling actually usable for the users. However, I think that it won't be part of Flink 1.2. I think that's still, I mean, 1.2 is due in, I guess, if we use the regular release cycle of 3 months in like 1 month or 1.5 months, this won't be the case. So I won't expect it in 1.2. But I hope that the community will start working on that soon, and using like the functionality from Kubernetes or from EC2. It might be not too complicated to do it. Just exposing probably the like make it easy for the user to configure if you when you run the job on Kubernetes, for example, that you define the metrics and the thresholds. But there's no one currently working on it. Yeah.
Last question. Yeah. One more question coming back to the key group thing. So if we have a parallelism of 10 and I have only 5 keys, and I said that I have 10 keyed groups, what happens with the 5? Are they empty or?
Yes. I mean, what happens is that we hash the key, and based on this hash value, we assign the keys to the key groups. And if you only have like 5 keys, of course, then at best they are distributed across 5 key groups, but the other key groups will be left empty. But usually you have more than 5 keys, and usually you have more keys than key groups. So every operator should be working on something. Yes. Yeah, thank you.